Yeah, so it's going to be based on this paper, which is on archive and hopefully getting updated soon. Yeah. So a quantum channel transforms a state into another state. And so transformations from input states to output states. And we're interested in them because many physical processes can be modeled in this way as transformations of states. So for instance, CV quantum communications networks, you regard the transformation of the thing you're going from the sender to the receiver as a quantum state, and you want to know what the loss is or some other properties of the channel. Same with things like optical computers. You can regard the whole circuit as a channel. So what does it mean to learn a quantum channel? So I'm going to talk in a very generic way, very agnostic as to how you're doing this learning. And basically, there are two kind of paradigms we can think of. One, but also others. So firstly, you could say, I have some experiment. I want to learn what this experiment's doing. So I send states through the channel. I measure these states, and then I make a classical idea of what the channel is. So on this classical computer, I have some classical knowledge of what the channel is, some description of it, mathematically or some other way. And so that could be one way, learn the channel, and then you understand so it's about learning the input-output relations, and we can then mathematically just figure out how another state would be transformed by using our mathematical model. Alternatively, we can have some quantum device, and we want to tune the parameters of it so it best imitates the target channel. So we have some target channel, and we have some learn channel, and by sending states through both of them and measuring how close the outputs are, we might learn in that way by minimizing the difference between them. In any case, what we want to do is want to be able to reproduce the input-output relations. And so that can mean a classical map or a set of parameters or anything else. By the way, feel free to interrupt me at any time if I'm being unclear. All right, so full characterization can be very expensive in terms of the number of samples you need to send through, and that's especially true when we're talking about continuous variables. And so generally, and also in continuous variables, you're forced to draw your inputs from a specific set of inputs. So, and in CV, we have generally an energy constraint as well as the fact that it's infinite dimensional system. So often we would probe channels. So this would be coherent states. So low energy coherent states. Set of coherent states of bounded energy. I don't know why my mouse is somehow I can't get rid of it. So okay. So right. So the way we construct our bounds is in three stages. So first one is kind of what I'm assuming to have already been done. This is just learning the channel in the low energy regime. So this is the part. So I'm saying we start from some bounds. I don't care how you got there. So you've got two channels that are close together for these low energy states. And that's what you know, but you want to then generalize what you know. So you've got these low energy states, and what you can say is that for any coherent state with an energy less than tau squared, so average photon number less than tau squared, the distance, the output distance is epsilon, less than epsilon naught. So I don't care how you got to this point. It's completely agnostic to how we got here, but this is what we're starting. Okay? And so our first step is generalizing to higher energy states. So we're going to construct this bound in two steps, or three stages. So first we got the in-distribution generalization, in that we know that for any state in this regime, this low energy regime, it's bounded. Then we say, all right, we want to construct some function that takes as an input how we're doing in this low energy regime, and strictly also takes tau, the size of the input of the energy probe over, but takes as an input this bound we have, and it takes as an input the energy of the state we care about, and then we can say, okay, for any coherent state, it's now bounded by this function. So we want to construct that, and then we want to say, all right, suppose we've constructed this, what about things that aren't coherent states? So now we say, okay, what about a squeezed vacuum? What about a Fock state? What about anything? So we're bounding it in these three stages. And, and I should say, yeah.
This is not distance.
This is trace distance, yeah. And that going back, I said, right, so there are two kind of goals here. One is we want to provide a usable framework so that if you tell me what state you have and what class of channels you're looking over, you can just apply it. And then I also want to give some very general bounds, which are going to be not good in terms of tightness, but they're so general that we can back say make some pretty broad claims across for all channel length. So, okay, so first thing to do, so as I said, with first, right. So first we're trying to construct this part. So going from low energy coherent states to higher energy coherent states. And what we want some certain properties of this function. So firstly, you can, it doesn't need to actually be an increasing function of the energy, because we can always think of counterexamples where it decreases. For instance, just a measure and replace channel where it's flat everywhere. But that's kind of trivial. So we're saying, all right, in those cases it's trivial, we don't care. But if it increases, we want to bound how much it increases. So, and there are certain properties we need, which are mathematically written here, but they're kind of explained here. So firstly, it should be a decreasing function of epsilon naught everywhere. That means that if I learn better in my low energy regime, that should mean that I know better in my high energy regime, or at least not worse. And then it should approach zero as epsilon naught goes to zero. So, I mean, so one example we might think of immediately is just the trivial function, which is in the regime where we know it, it's we just set it to epsilon naught. In the regime where we don't know it, we just set it to 2. But then that doesn't satisfy the approach, the fact that it should be approach 0 as epsilon naught goes to 0, because outside for the high energy regime, it's always going to be 2, even if we get it to 0, even if we get epsilon naught to 0. And this is a slightly better trivial function where we just interpolate using the data processing default. But so the specific function, sorry. Yeah.
So you want to always learn perfectly on the vacuum state?
No, I want to learn on some so I'm learning in this area, and I want to say that as I learn better in the high energy.
That means the other way around. Like I would have thought you want to you want to use
Epsilon of the end.
Sorry, epsilon naught is the error. So the quantities we need to remember are epsilon naught is just whatever error we can bound it to within this regime.
So you want to do better outside the region you're trained on?
Yeah, so no, so I want to say that outside the regime I'm trained on, if I'm learning better in the regime, then I'm also learning better outside the regime. So just like the kind of obvious thing you'd expect, right? Is that like, you know, if you're doing getting better in distribution generalization, if you're getting a lower error in the bit we're learning on, we should also be getting a better error on the bit we're not learning on. Otherwise, what's the point of doing more learning?
Yeah. It seems quite stringent. Like I could imagine that you're just doing better.
Yeah, just better.
It doesn't have to be substantially better.
No. My point is basically just that otherwise, I don't want is a situation where I go to a constant even when this goes to 0, right? So I don't want to get to a situation where even though I've perfectly learned it, which I can never do, but like as I get a lower and lower error, I'm not helping my bound at all. So that's the situation I want to avoid, is where I still know nothing about this, even as this just keeps going down and down. So, and in fact, so the kind of, on the next slide, I have an example of why this is not a trivial condition to say. So here is the care interaction defined by this unitary, e to the I kappa n squared, where n is the energy. And basically what we can find is there's this kind of weird behavior where it goes up and then dips. And so each of these kind of going down the rainbow, you get closer and closer together. So these channels are in theory closer and closer together. And yet, in certain parts of the regime, they're further apart, right? So for certain energies of coherent states specifically, they are further apart in what we see. But in fact, if we had access to all states, so in fact, they're more distinguishable if we use non-classical states. But the point is, from what we see, this is not the behavior we want, so this is why it's non-trivial to say that such a function should exist. Or at least, to me, it seems non-trivial. But we prove that such a function does always exist. So just going back quickly, okay, so yeah, we've got this trivial bound, and then we can also formulate for specific function classes this bound. So here's one that you can formulate for Gaussians. So just assuming that these two channels are now Gaussian and telling me that I have this tau and this epsilon naught, I can formulate this which goes for any energy. And then if I get a smaller epsilon naught, I've got this smaller bound. And eventually, if epsilon naught went to 0, it would just be 0. So the point is we can construct these bounds, and then the more we know about the channel class type these bounds are going to be, the more general we are, the less good they're going to be. And the other thing we need is concavity, and that's just because it's mathematically convenient, but it's also free in that I can just draw a concave half. If I've got some other function, I just draw the concave half. Okay, so the kind of non-trivial result here we have is that this exists. So any pair of channels, I don't care how non-Gaussian they are, how weird they are, this exists. I'm not, well, technically there is a constructive form, but it's terrible. So what you should be doing is constructing a specific bound for your channels. So it's always possible to find, and that's a nice guarantee to have. Yeah, and this is not entirely obvious that it should exist, or maybe it is to you, but to me it wasn't, because we have these weird things if you go non-Gaussian. Okay, so I'm gonna move on now to generalization to different types of states. So we've now done this part. So we've said that this part is always doable. And now I'm gonna say, given that we have this part, what can we do here? Yeah.
When I think artificial generalization,
Yeah.
I think of sort of multiplicative artificial generalization. Basically saying that the risk for one and risk for the other
As a factor.
is just some prefactor and not some constante. And what you're saying here is that the coherent states you can always do multiplicative.
With coherent states, I can always make this function, which I guess, I mean, that's not multiplicative. It's, I mean, the energy, sorry, the fidelity scales somehow as a, okay, so for a Gaussian, the fidelity scales as the exponential of some quadratic function.
If it's not multiplicative and it's additive, if your correction term is too big, that you're seeing fidelity greater than 1.
So, okay, so sometimes, so for Gaussians, it's never reaches 2. This pretty line here. But yes, if your channels are too far apart, then it will then, if you have for some other channel classes, this bound that exists will will become trivial. The point is that as epsilon naught goes to 0, it does converge. So the main thing is that if we learn better, the more, so if we have enough samples, we can make it non-trivial anyway. And that's a very weak condition, I agree, but it's something that is not obvious.
Then I can correspond to multiplicative. But we can move on.
I don't know if it's not, I mean, maybe you can make it into something else, but like, I mean, it's some function. It's not like,
So if it's operative, that if you're perfectly learned on one, you're perfectly learned.
Yes.
Is that true for your data?
Yeah, so if you perfectly learned here, this condition. It should approach zero as epsilon everywhere as epsilon more goes to zero.
Then I think that's more.
Right.
Could be more general.
Well, I mean, I think it's more general form. It's just something that converges to zero.
Okay, fine, but you don't have you don't have an active term.
Right, this is the entire thing.
I haven't been looking for it all active, I think I've got a big.
Sorry, yeah, so this is in fact the entire point is of all of this is to never have an additive constant.
Sure,
Right?
okay.
Is to always have something that will go to zero eventually. And it might be really bad, but it will go to zero eventually. And so in fact, so I've kind of phrased these conditions here. At any energy, if I make epsilon naught smaller, then epsilon naught then this function can't get bigger. And secondly, eventually it will reach zero. So it might, and in fact, what it can be is it can go to trivial and stay there for ages. Then if I make epsilon naught, it'll go trivial slightly later, etc. And again, this is a very weak condition, but the fact that it exists at all for all channels, including really weird ones, you might think, otherwise you might think there's some really non-Gaussian, really weird thing that doesn't obey this, but that doesn't exist. So we can say that, and that's this. Okay. Right. Okay. So now this is a fairly simple thing. So okay, suppose instead of a classical, okay, so I guess I should say in CV, what we call classical inputs are things with a positive P representation, which means they have, so a P representation is a quasi-probability distribution over coherent states, and every state in CV can be represented, every state can be represented as a quasi-probability distribution over coherent states. Quasi-probability means that it can sometimes be negative, but it still integrates to 1 across all states. And if it has a positive P representation, that means it can be represented as a probability distribution over Gaussian, over coherent state, over just a normal probability distribution. So if it has a positive P representation, like this thing here, which is not, so a coherent state is just a delta, a sign. And whereas this is something different, and so we might ask, okay, does this still hold? And yes. So we can just say, imagine that we have a coherent state with the same energy. That is as this classical state. Just take the bound for that coherent state. And this is fairly simple from the convexity of the trace norm and Jensen's inequality. So basically what we say is, okay, I can, it's less than or equal to the integral of the expected value of this function of ours over the classical probability distribution, and then the expected value of a function is the function of the expected value of the probability if we have a probability distribution and it's okay. So okay, this is fairly simple, but then we say, okay, what about states with finite negativity? So non-classical states. So all non-classical states are defined by having negative bits of their P representation. So somewhere in the P representation is negative. And so then what we call the negativity is the integral over the negative mass. So like the integral over all the negative parts, and this can be infinite. And in fact, for lots of important pure states, it is infinite. So I have here, but first we're going to look at the non-infinite case and then extend this to the infinite. So here we have a single photon added thermal state, and this is its P representation. So it's got a little spike at 0, but otherwise it's basically fine. And so it has positive and negative parts. And what we can do is we can split it into 2 components and then use the triangle inequality. So we can't directly use the triangle inequality because we have not a valid probability distribution. But I can say, okay, I can represent this as rho plus and rho minus, where these are supernormalized and subnormalized states respectively. And then I just normalize them and I do the triangle inequality. And then I know for each of them I have this bound and I use the triangle. Right? Any questions here? Okay, So, and then I can make a looser bound, but somewhat simplified, where instead I just take the absolute value of the P representation, and I calculate the same thing for that, basically. And this simplifies because we only need to calculate 2 quantities rather than 3. Sorry, I should go back and say, here, I need, so this n plus and n minus may not be, in fact, aren't the same as n bar for the whole state. So you should really calculate those as well as negativity. So the 3 quantities here I need to calculate are negativity and n plus and n minus. But maybe I don't want to do that, so I can, and so you might say, why use it if it's worse? It's easier, well, then I only calculate 2 quantities, and I'm going to use this later, so that's why. And here, this is the same state, but I just flip the negative spike, so this is the same. Okay, so now, what about infinite negativity? So squeezed vacuums have infinite negativity, Fock states have infinite negativity, many states have infinite negativity, and that's a problem because our bounds will contribute. But for any state with infinite negativity, it's delta close, so it's arbitrarily close to a state with finite but big negativity. And I'm going to make that more concrete later. But okay, so we can use the data processing inequality. So suppose I have some states that are some distance apart, and I pass them through 2 different channels, red and blue, and I want to know how far apart they are. Well, suppose I can calculate how far apart a different state is after passing through this channel. How can I connect these 2? Well, this channel, the blue channel, can't make these states, no channel can make states further apart. No single channel applying to the same two different states can bring those 2 states further apart. So the blue channel can't bring circle and square further apart. The red channel can't either. So I just add twice the, so it's just the bound I can calculate on the squares plus the distance on the grey squares, on the grey thing doubled. Right? So suppose I have some sigma with finite negativity that is delta close to the row with infinite negativity. I can apply this inequality. And now, but then so remember we don't want an additive constant. This delta looks like an additive constant because we'll never be able to get that to 0. But then we just pick another closest state. And I now need to justify the claim that there is this sequence of infinite negative of finite negativity states that can get arbitrarily close. So which sequence should we choose? Now our first thought might be convolution with of the P representation with a Gaussian. And the reason, so this is basically the same, this is equivalent to an additive Gaussian noise channel. And the reason we might choose this is because if this S equals half, this is just the Wigner function. And if this S equals 1, it's the Q function, which we know is positive for all states. So it's kind of a way of interpolating from negative states to classical states. And in fact, sometimes the minimum S required for this is called the non-classical distance. So okay, this is the first thought how we might do it. And then we can calculate this delta for the states after losing some S. And we should also calculate mu for our new state. Sorry, that's the integral over the absolute value of the P function for our new state, which is now going to be finite. And eta I have not yet defined, we have defined it in 2 levels. And the distance from right. And so then, why is this not enough? Because of squeeze states. And squeeze states have this funny behavior where this convolution doesn't change their negativity from infinite. It stays infinite until some threshold, at which point it suddenly switches to 0, which is inconvenient. So instead, we can also add in a truncation step. So now there are 2 parameters deciding our new state, which we'll call sigma. So there are now 2 parameters determining this new state. It's how high we make our cutoff and what S is. So I can always truncate to some finite Fock representation with capital N. and then I renormalize this to make it a valid state. And then I care about, okay, so this is kind of the normalization constant for this. And for any state rho, it's a distance less than this, where n bar is the energy of the state from the original state. So I just add these two, delta s and delta m together. But actually this can be tight for pure states, this is tighter. It's just 2 times square root of 1 minus eta m. But for mixed states, it might not be. Or there's a different bound. Okay, so then we have bounds for infinite negativity, which must, so we have this bound that has to be optimized over these two parameters, s and capital M. And in general, they're very difficult to actually do, but they exist. And we can eventually just take s to 0, m to infinity as epsilon or small, right? So, sorry, I don't know if I did define mu. It's basically just the integral, doing the same thing as mu, integrating over the absolute value of the p representation, but multiplied by r squared. So this is the energy of the new state where I just take the absolute value of the previous state. So this is the n bar basically for the state where I took the absolute value of the p representation. So okay, so we have this for, so if I put in my actual states, I can get an answer for this, I can get a function. But what if I don't know anything at all about my states, other than the fact that they have an average energy? So all I know is that my input has an average energy of n bar, and then it can be whatever I like. It can be some weird, tiny bit of a really high energy Fock state, and then maybe 0, or it can be anything. Well, I can very loosely bound. Okay, so firstly, if I know the Fock basis decomposition, I can bound the negativity. So these quantities using these expressions, which are not nice, but fine. So this is a gamma function, and this is the Oppenheimer symbol, and yeah. But and I can, the less I know, the more I need to in general in my bounds. And in fact, I can upper bound all of these upper bounds for any state without knowing anything about it other than n bar with this thing, this object, which I still need to tune over s and n, right? And that tuning depends kind of on what this function epsilon is, but it exists. And we can pick particular relationships between s and m to study different things. So if I set s proportional to 1 over kappa m, I kind of get an order scaling of this bound. And basically, although this is terrible, what it tells us is that if epsilon naught approaches 0, we can send m to infinity, and sorry, there should be a kappa, but basically I can send m to infinity and send everything to 0. So it's always possible to send this bound to 0 for as long as this thing gets smaller. So the smaller I make this object, this epsilon object, the bigger I'm allowed to make this object, this prefactor, which means I can make these two smaller. So the bigger m is, this is kind of polyexponential in m. So sorry, in s. In m. Making m big is bad for this factor. Making s small is bad for this factor. But I can do it if I make this small. And so the leading order term scales at most polyexponentially in energy, which is bad, but then this is incredibly general. This is saying that I don't know anything about what I've learned. I just know that I have some pair of channels that for a certain region, I know that the distance is close. And I can say this for any pair of channels, any state, and I know absolutely nothing about it. Right, so when should we use each bound? Well, if it's classical, negativity 0, all these quantities are 0, we just use the simple bound. If we have finite negativities, like single photon added thermal states, we should just calculate the negativity. in general, we always want to calculate things if we can, instead of using these bounds, because they're like they make everything worse. So infinite negativity that can be made finite with a convolution. An example is a Fock state, and preferably we should just calculate it again. Else you could use the specific things I gave for if you're a Fock decomposition. And the same with delta S, which I gave a bound for, but you should just calculate it if you can. Infinite negativity or infinite, so that can be made, infinite negativity that is still infinite with small convolutions, such as the spontaneous squeeze vacuums. Again, repeating myself, but preferably calculate it. Otherwise, use the Fock decomposition, or everything basically. And then if we know nothing, then we have to use these general rules. So I'm finally gonna give an interesting to me interpretation that I guess has nothing to do with quantum machine. But we can kind of treat this as a bound on the maximum advantage you could possibly get in a channel discrimination task, which is very slightly non-trivial, but mainly trivial, which is that, so if I had some channels that can only be discriminated with a tiny probability for low energy, for coherent states, then there's a maximum I can do with non-classical states, which is kind of obvious, but it's not trivial perhaps, because for instance, if you talk about QFR quantum Fisher information, that can be infinite for non-classical states, despite being finite for Gaussian states. So this is an interpretation that's almost trivial, but not quite. And so, yeah, so to conclude, it's always possible to formulate this bounding function for coherent states. So it is possible, good enough. And we can generalize finite negativity states with a cost that's, so this is basically multiplicative. A cost roughly linear negativity. There is a slight difference. You have this n plus and n minus, so that's a technicality. You still need to calculate that, but it's basically linear negativity. Generalized to infinite negativity states using the sequence of finite negativity states. So either convolution or truncation followed by convolution. And we can bound it for all states, which tells us that out of distribution generalization is always possible in the specific sense that if I have enough samples on this low energy subset, I can always bound it for any state. If I fix a state, I say I can bound it if I have enough samples, even though this may be a terrible bound, even though it may be very costly, it exists, and there are no weird niche cases where it doesn't exist. And that's kind of the takeaway message of the general bounds. There are no weird niche cases where you can't bound it. Now, what would be nice is to generalize this to multimode, which I think is fairly simple, but I have not done it and don't have time to do it. But this would be nice because then you could say something similar to this, but for the diamond norm instead of just the output tracing. Also, more specific bounds to specific cases, or either specific states or specific channels, and then tighten the bounds, which I think can be done a lot. And also, it might, even my truncation plus convolution thing may not be the best sequence of states, right? So it is a sequence of states that can be brought arbitrarily close to the target state, and that has finite negativity. It may not be the best in the sense of the negativity may scale a lot more than it needs to. Yeah. And I have a bunch of extra slides that people have questions.
I'm a bit surprised and confused by how general your claims that these related with possible. In the, let's think about a really trivial training ensemble that only talks about.
Okay, so this has to be greater than 0. So it can't just be nothing. It has to be a region, however small that region is, but it can't be
I mean, like when epsilon goes to 0, it's kind of like analytic information. like if you knew the function exactly.
Yeah.
Good.
So that, yeah, so
So
in fact,
it's like operating.
yeah, so in fact, from process tomography, if you know it's exact, so we know that if it's 0 in a region, you can just, because you know every gradient, you can know it everywhere. But what wasn't clear is that like if you're delta close to 0, how this error propagates, whether it's somehow like can't be brought, whether it's just some weird switch on off, whether it's 0. So we know that if it's in a finite region it's 0, then you have every differential of how it changes. And so in theory, yes, like we know that it should go that at exactly 0, it should be 0. What's not clear is behavior near 0. Near 0 in this small region. Yeah. Sorry,
I had a question about the proof technique. Is there a reason you use these P representations for states to prove everything versus like, I know it seems like a lot of the issue, not issues, but like a lot of the work went into dealing with the unbounded negativity of this representation.
You mean as opposed to Wigner?
Yeah, or yeah.
Well, then I couldn't write it out because I mean, like the whole thing comes from the fact that it's probability distribution, right? Over coherent, coherent states, and like I mean, a Wigner representation is not a probability distribution, right? Because I can't then treat it as coherent state. So even
I see. So
it's
P as soon as you make everything positive.
As soon as I make anything, as soon as I like convolve it at all, it's no longer a probability. It can no longer, even splitting it, be treated as this probability distribution over.
Yes.
Because I don't squeeze states have a positive Wigner in them. Sorry, all Gaussian states have a probability distribution.
Yeah.
And so clearly I can't just apply my bounds to squeeze state, right? So okay. Yeah.
So a bit complex, like to do generalized multimode. So currently, do the bound because you mentioned the diagonal, but currently do the bound for the trace norm you have multiple modes.
Sorry, say again. Do the bounds so the negativity function. Okay, so any state. So in that case, I'd have to say coherent. A P representation is a probability distribution over probability over multimode coherent states, right? And I mean, so firstly, I need to be careful in defining the region I've learned over in terms of like, would it be the total energy or like the energy per node? I think like, so there's a lot of like little technical things, but I don't think there's anything difficult because the negativity, the principle of just flipping half of a state is perfectly fine. What's not clear is firstly, what the epsilon naught, so how you define the initial thing. So I think, okay, so this would be fine. This I think would be fine, but you just need to be careful about how you define epsilon naught in the first place. Then infinite negativity, I think you basically just need you need to make sure that you're, I think, truncating to as long as you know that each Fock state is still can be made finite, then you're fine if you do the truncation thing. I guess you just need to recalculate what delta S is, because yeah, so this calculation you need to redo, and this calculation you need to redo. And I think that, and then other than defining the initial stuff a bit better, I think that's the most. And then you need to recalculate the negativity of these things. So you basically just need to redo all these the same calculations, but in a slightly different setting. To me, it doesn't seem like there's anything difficult there, but I've not had a look. Yeah.
I've already asked about that, so
I have a question about your starting point. And you go back to what you assumed initially about your approximation guarantee on low energy coherent states. Is this a worst case assumption? So you're saying for all
for all states in this, there are for all coherent states with lower energy than this, I know it's bounded by this. I can reformulate, so if I have some different thing coming from my model, from how I'm doing the learning, I can always reformulate it to something like this, maybe inefficiently, but.
What if I only give you a guarantee that holds with high probability over randomly wrong low energy?
I mean, I think you could use like Rademacher complex, or you could use some kind of in distribution guarantee. One thing
Yeah.
I said in the paper was, one technique would just be if you sample like uniformly over this, so you say no two states more than this distance apart, and again use the data processing on quality, and then as you learn better, you take samples closer and closer together. In theory, you can always finagle your like whatever you have into this. This is just, I was trying to be as agnostic as possible, and so this is kind of a very general way of phrasing whatever guarantee you have. You can redo everything with different guarantees.
But I should think of this as starting from a worst case guarantee and getting worst case guarantees. It's not starting from a general approximation.
Yeah. I think you could probably turn a general guarantee into a worst case guarantee, maybe with some overhead in this region. But and it starts from worst case going to worst case. But like you could probably redo all the stuff with different assumptions.
My same question. Oh,
Yeah. Sorry.
My same question.
Yeah. Okay.
My same question before basically. So do I understand correctly that the assumption that you're training something in this region
Yes.
super crucial? So if you just did
Oh, sorry. Really short.
if you just did box states 0, 1, 2, 3.
Okay, well, right, the fox states would work because so the main thing with coherent states is that they are no basis, even in a small region, right? In any finite region,
But you're playing the average generalization is always possible.
in the scenario where I learned in this region, I can always generalize. Okay, sorry.
You've not done the other way at all. You've not done I can.
I'm not on the other way around now. Okay. In the case where we have learned this, I can generalize this to anything.
Not. It could be
It could be
5 randomly chosen boxes.
No, it has to be a finite region in the phase space. But this is kind of a more physical interpretation because this is what we do, right? This is the easiest way to learn continuous variable. Well, this is what is often done in process tomography type things. Or if I just have a laser to do if I'm doing my learning with a laser,
Have you thought about using coherent state algebras? So as to have finite dimensional representation like spin coherent state of pseudo this kind of stuff.
if you know, said something about this later, but I never did it. No, I can't.
I think it might be a good idea just to check whether the dimension of the representation is relevant. Here it seems that the fact that you are in an infinite dimensional representation play a crucial role. So if you, for instance, consider spin coherent state as you are here, so you have this finite dimensional representation that can help a lot to understand the region. So just if you have time, just have a look through it. Could be basic.
And we need to read something on each. I'll have a look, thanks.
Yeah, so like if I was talking about if the continuous subset of state, then you are asking to learn all of them. But
Yeah.
I think this is something you can really check experimentally. You can sample from that and then you learn more.
Right, so what I was saying is first you can either use in distribution generalization guarantees, like the Rademacher complexity or something like that. Or you can use, if you uniformly sampled, you could say using the data processing inequality, two states that started a certain difference apart can't get that much further apart. So as long as I'm sampling and as I make epsilon more smaller, I just sample with distance epsilon naught, basically, or distance a distance that decreases with epsilon naught. So more samples. So yeah, your number of samples would go up a lot, but then yeah, it's possible to avoid it, right?
Okay. Yeah, thank you.
Also, I will say that if you have a specific channel model, it's a lot you need far fewer samples. So for instance, if it's a Gaussian, you don't actually need to do this uniform sampling. You can just sample a few states, and then you know from the fact that it's a Gaussian that it can only change. You know how it changes. Sorry.
What about the other direction? What did you learn from subfunction after school states? And then generalize.
There are other complete basics probably, but you have to redo a lot of stuff. If there are other complete basics, I'm pretty sure you can always do this technique. So this general technique of if you have this there's like probability representation in terms of it, then just use it. Is I think generic, but I mean the reason we go for coherence is firstly they're easy to do, and secondly they're physically motivated. Because I mean generally I would be learning from the easiest things, not the
Learning, the record I was gonna give you, like, we, learning on say a two mode squeeze state using entanglement, that you just need one of it.
I wouldn't need to go back, I would need to do the multi-mode thing first, I guess, to make it, so if you're doing two mode speeds, then it's multi-mode, right?
Yeah, if you get like fair stable choices, you learn just one copy of it.
Yeah, so I would need to then turn it back to, function first, I need to do the multi-mode thing, or someone needs to do the multi-mode thing, yeah. Anyway.
More questions or remarks? So this tank. So one thing for the speakers, if you want, I will predict your bills. Otherwise, we have to send by, so by the end, we also the risk at this. So